Yeah, so we have time for questions.
In the beginning, you had this energy flux graph, right? Energy flux for different geographical regions, polar region, tropical region.
Yeah.
Can you bring that back again?
Yeah, sure.
Earlier.
This one?
Yeah. So here in the polar region, the total flux is negative?
Yeah, there are some, I guess there are on average some areas where there is a net transport of heat from the atmosphere into the surface, which I think is the reason why there can be a negative flux.
But there are only a few. But and as you can see, this is also where our simple approach actually doesn't, where the annual mean doesn't predict the limit very well. But that means we need to take more specific information into account. So, for example, when you go to the pole or in the extreme high latitudes.
But the poles are supposed to be cold, no? So how can they give out more flux? They don't absorb heat; they give out heat. That's what you are saying, no?
No. This means that the transport of heat goes from the atmosphere to the surface.
Okay.
And that's being sustained because the atmosphere transports heat from the warmer regions to the colder regions.
Okay.
And then can put some in. Yep.
Thank you.
So on slide 13, while explaining the thermodynamic direction, did you say that entropy is increasing all the way from sun to earth?
I mean, here the entropy is the entropy flux increases because the temperature decreases. Then through space, nothing happens. And then at Earth, being absorbed and re-emitted, it also produces entropy. And then again, when it is emitted from Earth, and the thermal radiation that then travels through space also does not produce entropy. And then in principle, there is a potential to further degrade this from the Earth's radiative temperature to the cosmic background, or the temperature of the cosmic background radiation.
Yeah, but in sun, because of nuclear fusion, there is a huge loss of heat, and as per Clausius, that lead to gain in entropy should be very high in the sun, and perhaps that is the reason why there is an order on Earth in form of life forms, like plants are ordered structure because there is a gain of entropy in the sun. Isn't it true?
No, I think it's slightly different, and that is, the entropy, or the radiation that is emitted from the sun at a high temperature is actually low entropy and not high entropy. And that is because you have a certain amount of energy, and when you have a given amount of energy at high temperature, the expression is basically proportional to energy flux divided by temperature. So when you divide by a high temperature, you have a low entropy flux.
But heat loss is very high in that reaction, nuclear fusion reaction.
Inside the sun?
Inside the sun, yeah.
Yes.
So wouldn't that cause very high entropy in sun?
No, it actually it actually produces very low entropy because, as I said, it's 1/T. Yeah?
Yeah, so Q is high. Q by T, right? Q is heat.
Yes.
And Q is very high.
Yeah.
So
the Q is very high, but the entropy flux that leaves the sun is proportional to the heat flux divided by temperature. Yeah? Okay. So heat flux by temperature, and if the temperature is really high, then it's a low entropy flux.
Okay,
yeah?
Thank you.
And you can actually also, in terms of radiation, you can actually also visualize this difference in entropy, is that when you calculate how much a photon, or how much a solar photon on average carries in energy, then you have actually that you have a wavelength of about 500 nanometers, and the radiation that is emitted from the Earth is 11 micrometers. So it's a ratio of 22. And so what this essentially means is that for each photon that comes from the sun and is being absorbed, there will be 22 photons carrying the same energy that's leaving the Earth. And so you can think of this as, well, you know, you distribute the radiative energy over more photons, so it's a higher entropy. Yeah?
Yeah, we have
my question is, that you said that plants, because of photosynthesis, they generate around 200 terawatt, and humans consume around 26 terawatt. So where does the rest of the energy go?
Well, you know, I mean, natural ecosystems live on that, right? I mean,
Okay.
So when you look at, perhaps I can just show this map. Where was this? This one, yeah? So, you know, when you have natural ecosystems, you have food webs, and these food webs are actually driven by the energy from photosynthesis, right?
Okay.
So first, about half of what's generated by photosynthesis is consumed by the plants themselves to grow, to maintain themselves, and to reproduce.
Mm-hmm.
The other half is half of it is created used to create biomass and so on, and then the other half is stored in the form of carbohydrates of, you know, wood or tissues and so on, and then, you know, the fauna, animals, you know, they live off that energy, and so they meet their metabolic energy by consuming the chemical energy from the productivity of the biosphere. And so the food webs basically draw upon this 220 terawatt. Yeah, so for example, also in the ocean you have the same thing.
Mm-hmm.
You know, the fish, they all relate back to the photosynthesis by the plankton, right? That's where they basically get their energy from.
Okay. So if you said that we'll have probably in few years some technologies that will about solar energy, will generate that energy. So how will we release that energy into the biosystem?
In terms of photosynthesis, or?
Yeah, so we can't just release energy. If we randomly release energy, it will be useless. It should be used by the energy. If we release it too much, it will not help anybody. It will just kill up everything. So if we generate the energy, extra energy by our solar energy, how should we release it into the biosphere?
Okay, so when we use solar energy and, you know, we consume it, then we basically don't give it back to the biosphere, but we produce heat, right? And then, I mean, this is something that, you know, it's an effect that's known in meteorology as an urban heat island effect, right? I mean, where we consume energy, we can actually also locally heat the environment. And that's, for example, why cities are typically warmer than rural areas, right?
Okay.
And so, and then once we consumed it and converted it into heat, then, you know, nobody can eat it anymore, right? Because it's energy of high entropy. It's already brought to the environmental temperatures of perhaps 20 or 30 degrees centigrade or 300 Kelvin. And so then you can't do photochemistry with it anymore.
Okay.
And you can only convert it physically by, you know, it drives convection or something, but you cannot return it to the biosphere.
Yeah.
Yeah.
So my question is, if we use photovoltaic cells and we make a lot of big, if we cover the desert areas where there's a lot of sunlight with these solar panels, how is it going to affect the energy which we'll be getting, generating a lot of free energy? How will it affect the climate of the Earth?
Okay, that's a very good point. Now, the thing is that most of the solar, quite a bit of the solar radiation is being absorbed at the surface and converted into heat. What photovoltaic does is it absorbs solar radiation but converts part of it already in electricity before it's converted into heat. So that's actually an effect that would almost not do much to the climate system. One can actually also think about having that almost like climate neutral, the effect. And I mean, the other part of it is that you don't need that much area to meet the human energy demand from, say, photovoltaics. I think I calculated once it's about 150% the area of Germany, but you know, Germany is not very large, you know, and so you wouldn't need so much area to really cause global effects. Yeah, and because solar radiation is absorbed anyway, but you can think of it actually, let's put it another way, you know, I mean, when you have wood, you know, you can burn wood and just look at it, or you can burn wood and convert it into electricity, right? And this is sort of a similar comparison. At the moment, you know, we absorb solar radiation, and most of it doesn't do anything except heating. Yeah? And we can use it much more wisely and convert it into electric energy using photovoltaics. Yeah? And so it's actually something that doesn't interfere so much into the system. While actually the other form of renewable energy that was also quite large is wind energy, and that's something where, you know, when you go to large scales, you affect the wind speeds, because every turbine takes kinetic energy out. And I'm actually now working in a project where we can actually show that this is actually taking place at quite a relevant scale, even in regional or national plans of renewable energy. Yeah, so in that sense, actually, using solar energy makes more efficient, or using photovoltaics makes more efficient use of solar energy, while all the other forms of renewable energy just take out energy that was already generated by some physical process. Does this make sense?
Yeah, it does make sense, but I also asked that solar panels are located. The solar panels are located, in a particular area. So even though this absorption generation of free energy won't do much to the global climate, will it do something to the local climate?
You know, I think it can, right? Because you alter the land surface, right? I mean, usually when you have like a lawn, it can evaporate and transpire water. Photovoltaic cell doesn't, you know, because it's glass surface or something. On the other hand, you know, especially in urban areas, we already seal off quite a bit of land surface, right? I mean, you know, we have streets and we have parking lots and we have a lot of roofs. And so if one would just use roofs, facades, and cover parking lots and so on, it probably would already be good enough to produce a significant amount of energy. Yeah. For example, we sometimes travel to Italy, and there on the freeway there are some parking lots, and they have like little rooftops to create parking lots in a shade, and on that rooftop are solar panels. And I think, well, that's pretty clever, right? So you provide shade, and you create renewable energy. So I think it's like a win-win situation, right?
We'll take one last question.
Sir, according to the second law of thermodynamics, the entropy should get maximized. So why the DNA form from the nucleic acid, because it is well ordered, or why the fractals are present in the nature, just like in the sunflower? It means why there is order in the nature always?
Well, I would say that you have order in nature because you are able to perform work. Yeah, because, you know, when you want to sort things, or, you know, earlier when my son was little and he played with his little Lego bricks, I don't know if you know those, you know, I mean, they're quite painful when you step on them. But typically what happened is, you know, you needed to perform a lot of work to tidy up his room, right? And so you create order by performing work. And we are able to perform work because we are in a non-equilibrium system where because of radiation, you have a large difference in entropy fluxes at the planetary scale. And from these difference in entropy fluxes, we can derive our work and maintain low entropy systems.
All right, if there is no other question, let us thank Professor.
Well, thank you for your
this nice talk.
attention. Well, thank you for your attention.
And this is a small token of appreciation from the Institute.
Okay.
Thank you for such a nice talk.
Yeah, thank you.
It's nice. Thank you.